So in part 4, we're actually going to use the same equipment to attempt and model the human eye as a lens screen system. So as you'll note in your lab manual, it wants you to place the lens with the longest focal length. In this case, it'll be lens 1 in the holder in position and position the screen so that very distant objects will come into view. So if we put this guy here and we can change our screen so this shows up well?
Very good. Yes.
Okay. To try to get very distant objects to come into view. And this setup here represents the model of the human eye when it's at rest. And that is when the eye is focused on the horizon. In a real eye, the lens is actually located behind the cornea. And I have a little model here to try to show you what I mean by that. So if we take away the layers of the eye, and if we notice that there's the cornea right here in the eye is actually the boundary where most of the refraction of light occurs. It's this lens in its location right behind the cornea that allows there to be some more fine adjustments. So I want you to realize that in this model, the lens does not change. As it doesn't change in real life, the position of the lens does not change. And so we're going to attempt to maintain this lens position for our model of the human eye in this setup, as it is with a real eye. So we've got distant objects in focus here on our retina on the screen, and this represents the eye when it's at rest. You'll notice in your lab manual it says it wants you to now return the light source. So we're going to use this light source to focus on a closer object. And you'll note that no matter where I have this, I'm unable to focus this light on the screen. The lens of my eye has not adjusted its shape to change its focal length and allow closer objects to come into focus on the retina. So I'm going to model a change in shape of my lens by replacing it with my shortest focal length, number 3. And you'll note now that I am able to bring closer objects into focus on the screen. And we kind of saw that this was very similar to what we had with the camera model. And the human eye is very similar in its basic structure to the structure of a camera. So I'm not too surprised to see that we have some similarities between these two models. If the image that forms on this screen is a bit washed out, because there's a lot of light here, it's usually the result of extraneous light that's coming in through the lens and on the screen. It's light that isn't necessarily used to form an image. And so in bright light situations, the pupil in the eye will actually constrict in order to limit the amount of light that's actually able to make its way into the eye and onto the retina. And we can simulate this constriction by using the aperture wheel that we have at our disposal. And you'll note in your lab report, it wants you to place the aperture wheel on the optic bench between the source and the lens. And that should make sense because that's where, in the model of the eye, we actually have, as you'll note, the pupil itself comes in front of the lens of the eye. So we'll mount this here. And I'll start it on its largest aperture setting. Okay, and it really hasn't changed in terms of its brightness. But and actually, what we'll do here is let's turn off that light. So what we've actually done is we've shuttered the windows here so that we can only have the light from the room, the ambient light from the room, and that from the object here. And now you can really see that this image on the screen is relatively washed out. And so what we're going to do is we're going to, step by step, we're going to limit the amount of light that comes through this aperture. And in doing so, we're going to model the constriction of the pupil. So as we go from our largest setting, letting the most light through, you can see it kind of get washed out around the 4. And as we restrict that light greater and greater, we'll find that the image itself gets crisper and crisper. However, that might have been our lowest setting. We got one more here. And so we end up getting the image that is the sharpest image. this still looks substantially different from what we had when our aperture was on the largest setting. You'll note that while it may be sharper around the edges and we've eliminated that washed out light, that unnecessary light that doesn't go towards forming the image, the overall image itself appears to be significantly dimmer in comparison. And that should make sense. We're restricting the amount of light that's coming through here. And to try to show you what the setting is on this aperture wheel, it's relatively very small, significantly smaller than the object itself. And so you'll notice that we'll still be able to form an image on the screen, but it appears to be not nearly as bright as it was in the first case. And we're still getting those light rays that come from the top and the bottom of the image to pass through that little pinhole and then pass through the lens and converge on the screen in the background to show an image. So again, when we're on our largest setting, we'd still get an image that's bright but a little washed out. But as we restrict the amount of light that we're actually able to allow through that lens, we get a crisper image that's significantly dimmer. So continuing in part 4, now moving on to really putting an emphasis on accommodation. And the experiments that follow, we're again going to make sure we leave both the lens and the screen in fixed locations to try to simulate, again, the lens of the eye and the retina. So these won't move in our model of the eye. And we're going to insert different lengths, different focal lengths rather, different lenses with different focal lengths at the same location to try to focus on objects at varying distances. So the first thing we'll do, you'll see in part 4, step 7, is to ensure that the light source is off and removed, and we've done that. We're allowing light from the window to reach our screen, and then we're going to simulate accommodation of the lens with our model eye by first placing the long focal length lens in this position, and then we're going to switch to shorter and shorter focal length lenses. Again, I'm physically going to be removing one lens and putting another lens on, but in the human eye, or really almost nearly any eyeball it should be, the lens itself is going to be the same. It's just going to change or accommodate its shape. And there's a good discussion about this in the lab manual. If you follow through with this, it describes what's happening with the ciliary muscles that surround the lens that allow it to change its shape and focus on objects at different distances. So with our longest focal length lens here at this location, again, get a pretty crisp image of the outdoors. It's a bright day, blue sky, the outline of the trees. But if I have something that's closer, notice that it doesn't come into focus. In the camera, we were able to move the lens and change its position. We can't do that with the eye. And so what we're going to do with our eye that we can't do with the camera is we're going to change the shape of the lens. And to model that, we'll put this at the same location. And now as you see on the screen, I'm able to focus on the hand as I was able to with the camera, but in a different way, using a different method to try to get this. I'm able to focus on a closer object. And now the background is what is blurry and out of focus. And for objects that are even closer, I can change the shape of my lens yet again. And so, and this one's a little more difficult to see, but if you can see as I move my hand in front of the lens, the shape of my fingers and the web in between my fingers will show up on the screen as a crisp outline, and I'm much closer. Now, there comes a point where I can no longer focus on objects in front of my eye. Regardless of what my eye does when it's in its most relaxed state, or if it's if the muscles are at their greatest contraction, I'm not able to get these images into focus. I am past what is referred to as the near point of my eye. And you'll note that in your lab manual, it discusses the near point of the eye as the closest point in which you can focus clearly on an object. And it represents the maximum bulge that the lens can achieve. In young folks, this is usually a relatively close distance, somewhere around 10 centimeters, and that image will recede, that image distance rather that you can focus on, that distance will recede with age. It's in general, it's a consequence of the eye's inability to continually change its shape as we age and get older. So the gradual loss of accommodation with age reflects the lens's changing elasticity, as it states in the lab manual. In many folks over 50, the lens is no longer accommodating a condition that's known as presbyopia. In other words, the lens can no longer make those small adjustment changes in its shape to change the focus. And at that point, additional lens accommodation is required. So the use of reading glasses might be more effective at getting an image to focus up closer. So to measure the near point of our model eye, we're going to place the lens with the shortest focal length, which I already have here, lens number 3. And we're going to use the light source now as the object. Measure the distance of the object from the eye's lens when it has reached the nearest point that we can get this thing to come into focus. So this is lens 3 is the maximum bulge we're going to be able to achieve. And so as I move this closer and closer and closer, I get to a point where I am able to form an image on the screen, but past that point, it'll just be a blur. I won't be able to get that image to come into focus. And so the near point of my model eye here on the optical bench can be measured by finding the distance between the object and the lens. Now, using a ruler or similar device, measure the near point of the eyes of your group members. So in this case, for our first group member, to measure the near point, we're going to start with the paper far away from the face, so you can start with it out here. And the light will come over the shoulder, bounce off the page, make its way to its eye. And we're just going to measure, as best we can, the distance from the front of the cornea to the paper itself. And I'm getting a distance, if I take into account that part, it's about 14.5 centimeters. So that was where it could focus? 14.5 centimeters. Okay. Huh.
Still is clear.
All right, so we'll do it for me now. So the final part of section 4 in this lab experiment, which models the human eye, is going to take a closer look at the defects that are common with the human eye, namely hyperopia and myopia. So we'll focus on those two terms. Hyperopia, or farsightedness, is the condition where the eye has no problem seeing objects that are really far away, but it does have issue with focusing objects that are relatively up close. And this is a common condition for folks as they get older and the eye loses its ability to accommodate. They can still see perfectly fine away for objects that are out in the distance. That parallel light comes in and comes into focus with relative ease on their retina. But for objects that are closer up, the eye can no longer accommodate as well. And so those objects don't come into focus. And so those objects will end up focusing too far behind the retina. So to model this, what we're going to do, we'll model the defect and then we'll model the correction of that defect. So to simulate the condition of hyperopia, you'll notice that it says in your lab manual to take the medium converging focal length lens, and we're going to put this on the bench and we're going to move it so that we can get an image on the screen. And it's a clear image. But you'll note in your lab report it says, first bring the light from the source object into focus on the screen, then move the lens just a little bit closer to the screen. So we've got this object in focus, and now we're going to move it a little bit closer. And it asks you to think, what are you doing here? Regardless if this screen is here, that image is being formed somewhere. In fact, I can use my hand to kind of catch where that image is being formed. The actual image is being formed here, which is behind where my retina is. So this image is being formed too far behind the retina. What we need to do is shorten the overall focal length of that light to have it to converge on the screen, in this case modeling our retina. The next thing we're going to do is we're going to take a second converging lens, lens 1, with the longest focal length, and we're going to put it between the light source and the primary lens, and we're going to manipulate the positions of the light source and the secondary lens to try to get an image to form on the screen. In fact, we kind of have good luck there. So again, this is the lens in our eye, this is our retina, and this is the corrective lens. It's a converging lens that converges light even further from what this primary lens is already converging. So without it, you'll see that image is no longer in focus, but with this secondary converging lens, it shortens that focal length. So the two lenses together act as a large refractory powered lens, and it shortens that focal length. So without and with, we're able to see the difference. We're shortening the focal length. Again, if we were able to accommodate or able to move the lens, we could bring that image into focus on the retina, but this image is being formed too far behind the retina. And this converging lens shortens that focal length to bring the image into focus on the screen. The second condition that we're going to model with our eye on the optical bench is the condition known as myopia. Myopic individuals have no problem focusing on objects that are relatively close. They still have the ability to accommodate with their lens. However, objects that are far out in the distance will no longer come into focus on the retina. Their eye, the lens in their eye, is focusing light too far in front of the retina in their eye. So in your lab manual, it suggests that you start again with the medium focal length lens, and you'll bring that object into focus on the retina, on the screen. And once you've done that, you get a nice crisp image. This is what a normal functioning eye would do. It would form an image at this location. But what happens is, it's usually due to the shape of the eye itself, the image itself will now form too far in front of the retina. And so once again, we get a blurry image as we did with the hyperopic eye, but for a completely opposite reason. Instead of the light focusing too far behind the retina, now the light is focusing in front, and I can get that image to kind of form on my finger. This is where it should be forming, and yet my retina is all the way back here. So what do I need to do is I need to extend the focal length of this system by using now, for the first time in our experiment, we're going to use the diverging lens. So that diverging lens will take this light that's coming in and it will kind of bow it out. Those light rays will diverge. They'll hit this converging lens and then they'll start to converge again. So it kind of adjusts that focal length. So here I have my myopic eye unable to cause an image to come into focus, but by putting the diverging lens in between the object and my primary lens, my primary converging lens, I'm able to get an image to come into focus on the screen. Again, so without, it's not in focus, and then with, I get an image that is in focus. And I'm able to change the overall focal length of this system by using a diverging lens.